The physics of light will be covered in several segments. Segment 2 covers the basics of light and color. Segment 3 is on mirrors and lenses. And Segment 4 covers the prospects of invisibility and the speed of light. In this segment, we will answer the 3 questions: why is the sky blue? What makes rainbows? And what is the difference between light and pigment colors?
Why are the skies blue? Some say it's because it reflects the ocean. If that were true, then the skies over Kansas, in the middle of the United States, and over Switzerland, in the middle of Europe, wouldn't be blue because there are certainly no oceans there. But the skies are blue over Kansas and Switzerland.
Light itself is really not well understood, and there are competing theories as to what light actually is, where it comes from, and why it acts as it does. Even when the Bible talks about light, it is strange, because in the book of Genesis, which records the creation account, light was created 3 days before the sun and the stars, which means that, according to the Bible, light is a fundamental component of the universe and exists apart from a visible source to generate it, which pretty much agrees with what modern physics says about light. We will look at the conflicting ideas on light when we get to our Physics of the Weird segment. The current theory of light says that at the atom level, light is a form of energy. In fact, a vibrating pattern of wave energy closely related to electricity. The idea is that electrons change energy levels, going up when energy is added from the outside, and then losing that energy. And when they drop in energy, where does the extra energy go? It is given off as visible light. A wave of light energy is produced. And this is happening trillions of times every second in every atom, creating the light we see around us. In other words, light is a natural byproduct of electrons vibrating back and forth, increasing and decreasing in their energy levels. The lost energy isn't really lost. It is given off as visible light. That's the basic theory of how light is produced at the atom level. Light acts as though it is traveling like an electrical energy wave, traveling through space, similar perhaps as water waves travel through the ocean. The color of the light is determined, incredibly, by the length of that wave. Seriously, longer waves appear to us as the color red. If you stretch the wave a tiny bit, it disappears from our sight into infrared. Infrared means under or below red, and our eyes are not designed to detect wavelengths that are that long. Red is the first and longest wavelength that our eyes are designed to detect. As the waves get shorter or closer together, our eyes detect the changing wavelengths as different colors, from red to orange, yellow, green, then blue, indigo, and finally to violet, and then to ultraviolet, which is now a wavelength too small or short for our eyes to detect. Now, before we go on, let's talk about this color, indigo. Sir Isaac Newton is responsible for indigo being the 7th color. He did much of the groundwork on the nature of light, and he saw 7 colors in the spectrum, with indigo here. But many people do not see a real distinct color between blue and violet, and they often list only 6 colors in the spectrum. So when all these waves are blended together, red, orange, yellow, green, blue, indigo, and violet, we see them as white light. These waves are very, very tiny, by the way. The length of any one of the color wavelengths is at least 50 times smaller than the width of one of your hairs. That's pretty small. Notice that the waves themselves are not colored, any more than electricity is colored. Our eyes are engineered to detect specific size electrical waves, and our brains interpret those waves as different colors. The waves themselves are colorless electrical energy. Light travels in a straight line, and your eye picks up those light wave signals if they are reflected off something like trees and leaves, or if they come directly at your eye from a source like the sun, or a man-made source like a flashlight, like this flashlight, screwdriver thing. If the light wave runs into something, it reflects off at an angle and continues on. That's why you see the leaf. The light reflects off of the leaf and enters your eye, transfers the electrical impulses through nerves to the back of your brain, and like a computer, it reads the information and you see the leaf. But the light has to hit the leaf and reflect into your eye for this to happen. Now, back to why the sky is blue. The air in our atmosphere is full of very small particles, including air molecules, dust, and tiny water molecules. The light waves tend to all pass by these tiny obstacles, but by the time you get to blue waves, even though they are 1,000 times bigger than air molecules, they are small enough to interact with these particles. As a result, when light enters the atmosphere, a small percentage of the blue and violet wavelengths electrically interfere with these objects, and they are scattered off at an angle. The rest of the light continues to the ground and reflects off of objects, making them visible. If our eyes were very sensitive to indigo and violet, the sky would probably look purplish. But our eyes are more sensitive to the blue wavelengths, so when you look up into the atmosphere, you see this, a glow of scattering blue light. It gives the appearance of a kind of blue shell that we call the sky. This reflection of light is often called Rayleigh scattering, and it is named for John William Strutt, the 3rd Baron Rayleigh, which admittedly is a pretty odd name. Rayleigh is actually a geographic area in Britain, and because of his accomplishments, John Strutt was given a sort of title of nobility over that geographic area. And he liked it so much that he decided to use this as his last name, as in Lord Rayleigh, which is why this phenomena isn't called Strutt scattering, it's called Rayleigh scattering. John also discovered the element argon, which is kind of cool. The blue-sized light waves are small enough that the air molecules actually force the blue light waves to deviate from their straight path, scattering the blue and the violet light at slightly different angles, giving us a blue sky.
Blue light scattering is the basic theory as to why the sky is blue. You can take this same theory and apply it to several related questions to answer them also, like, why are sunsets red or yellow?
As the sun sets, the light must travel through thicker or more atmosphere. Thus, more and more of the smaller wavelengths of light scatter off and never reach our eye. But almost all of the longest wavelengths make it through all that atmosphere. The reds and yellows are transmitted to your eye, while much of the other colors are reflected off. Plus, if there is extra dust or smoke particles in the sky, these will add to the red effect.
Why are clouds white? Clouds are massive collections of tiny, tiny liquid and frozen water droplets. These droplets and crystals are large enough to scatter the entire spectrum of light colors uniformly, and so the clouds look white. If they are very dense with water, light cannot penetrate, and they look dark. By the way, clouds are really heavy, but they are spread over such a large area, a large volume, which is why they float in the air. An average puffy cumulus cloud, about 1 mile long, contains about 500 tons of water. That's over 100 elephants' worth of water floating over your head. Why is the ocean blue?
Although small quantities of water look colorless, when you get huge quantities of liquid water, it displays its true color. H2O has a slightly bluish tint. The true color can be affected by algae or mud, and large bodies of water can reflect the color of the sky above them, getting grayish or green, or even red. But H2O was created in the beginning with a slightly bluish tint.
Why is the moon's sky black during the daytime? When astronauts were on the moon, it was on the sunny side during the moon's daytime. Then why is the sky always black? It's because there is no atmosphere on the moon to scatter the light. If the moon had an atmosphere around it, it would look like this. And from the ground, the sky would look like this. Back on Earth, if we took the atmosphere away from the Earth in daytime, the sky would look black. Black as in the daytime on the moon. Notice that in this scene, the light is still coming into the Earth because it's daytime, and it is bouncing off all the trees and the water and the buildings, but there is no scattering of light in the atmosphere, and so the sky looks black. And why can't you see stars? Well, you could at night, but in the daytime, the sunlight is scattering off all of the objects, drowning out the starlight. The same thing happens in the city. The bright lights scatter off all the objects even at night and drown out the dimmer starlight. Why is the sun yellow?
From space, the sun looks white because it is white. Actually, our sun is a star with a slightly yellowish tint, but it is so bright that it produces enough light to saturate and overwhelm all of your eye receptors, and it often looks pure white, even from Earth. At sunset, you will often get yellow or red suns as the blues get scattered. But why you often see a yellow sun at high noon on a clear day is still a bit of a mystery. What makes rainbows? Well, the simple answer is that rainbows appear when raindrops, acting as millions and millions of tiny prisms, reflect sunlight off into your eye at very precise angles. Simple. Okay, maybe that wasn't so simple. In physics classes, people often ask, who is Roy G. Biv? Roy G. Biv is the name given to the 7 colors of the visible light spectrum: red, orange, yellow, green, blue, indigo, and violet. People often use the word rainbow to mean whenever white light is separated into the light spectrum of Roy G. Biv, whether it's coming from rain or even a prism. By the way, if we got rid of the color indigo, then Roy doesn't have a vowel in his last name, so clearly indigo belongs there. Whenever light passes between 2 mediums, like between air and water, or air and glass, it slows down and bends. The difference between the 2 mediums causes a slight delay in the light wave's speed, forcing it to bend out of its normally straight path. Of the 7 colors in the visible light spectrum, red has the longest wavelength. As a result, these long waves don't take the corner in the bend as tight as the smaller blue light wave does. This difference in light wavelength causes the 7 colors to spread out and separate when they bend. Each color emerges from the raindrop at a slightly different angle. A real rainbow, caused by rain, occurs when the sun is behind you and the rain is gently falling in front of you. The correct angle for the sun usually happens later in the afternoon or very early in the morning. The gently falling raindrops act like millions of tiny prisms falling from the clouds and separating the light spectrum. When the sunlight goes from the air and enters the water of a raindrop, it bends, just like in a prism, and the light slows down, separating the colors as they move out of the raindrop at slightly different speeds. The colors reflect off the inside of the drop twice, then exits. Each color exits at a slightly different angle. It is these slightly different angles that cause us to see red drops higher up, then orange a bit lower, then yellow, then green, blue, indigo, then violet, which bends the most and is seen as the lowest part of the rainbow. Each falling raindrop flashes its particular color to the observer for just an instant before another drop takes its place, giving the rainbow the appearance of being still in the sky. This is similar to how a movie is made of hundreds of still pictures, which move and flash for an instant in front of the lens, giving the illusion on the screen of being a single moving picture. At this point, you might think that this kind of physics would simply produce a straight wall of color spectrum in the sky. I did. But why do we see a semicircle bow of color? Well, We mentioned that each color is coming in at a particular angle. An angle measured from a line connecting your head and the sun to the top of the rainbow. Red is at 42 degrees. Violet is at 40 degrees. And all the other colors are at angles in between those two. So if I'm looking at a rainbow, 42 degrees from me is right here. And 42 degrees is also here, and can be found here and here and here. But it isn't here. That isn't 42 degrees. But there is a 42-degree angle all the way around me, and if the ground wasn't here, you could go all the way around in a circle 42 degrees. Then drop down to violet at 40 degrees. Here, 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 here. The same circle and the other colors are in between. This arc of angles produces the bow rather than a straight wall of color. A secondary rainbow is often seen above the primary rainbow and is caused when some of the light reflects a third time inside of the raindrop, exiting higher and fainter and inverting the order of the colors because of the angle they exit the raindrop. Because the rainbow is a light image and not a physical object, you can never reach or touch the light image, but you can touch the raindrop in a similar way that you can touch a mirror, but you can't actually touch the image produced in the mirror. Other places you can see rainbows formed are fountains, or in the ocean as waves crash against the rock, creating mist in the air. Waterfalls, sprinklers, and mist from a garden hose. You can touch the water drops, but you cannot touch the light producing the rainbow. You can easily refract light and break it into the color spectrum using a mirror submerged in water, provided that the sun is at the appropriate angle. Or by spraying a hose with the full bright sunlight behind your back. Not every full color spectrum is a rainbow, though we often use that word to describe the color spectrum when we see it. We know that the rainbow is produced when light is bent as it goes from air to water or air to glass. This is called refraction. Halos can appear around the moon or the sun when light bends or refracts through millions of tiny ice crystals that are suspended high in the sky, forming a circular rainbow or white ring. Sundogs, or bright spots, can often appear on the sides of the halos. A glory is a rainbow-like phenomena that makes a rainbow halo around the shadows of the observer's head. The glory can only be seen when you are directly between the sun and the clouds. It is often seen from airplanes with the glory surrounding the airplane's shadow on clouds. It is similar to how rainbows are made, but the real mechanics of a glory are not well understood. Rainbows, or spectra, can be seen when oil is in the water or in soap bubbles, giving them an iridescent look. This is from a mechanism called thin film interference. It is called thin film because the thickness of the bubble, or the oil layer, is just about the size of a light wave thickness, pretty thin. The light reflects off the top of the film first, then travels down and reflects again off the bottom of the film. As a result, They emerge at slightly different times and run into each other, interfering with their light waves. Some of the wave colors are canceled out. Other colors get enhanced as they mix and merge together. The colors separate from the white light just like a raindrop, and they swirl around depending on the thickness of the film. Crepuscular rays, or sun rays, are glorious shafts of sunlight bursting forth from a cloud formation. Crepuscular is a Latin word that means twilight, as the rays often appear in the evening. They are essentially cloud shadows made by gaps in the clouds, allowing sunlight to stream through. You can also see them through trees when there are very small drops of water mist, fog, or dust scattering the light, making shadows. The rays are actually parallel, but they appear to fan out. This is an illusion of perspective, the same way railroad tracks look like they join together in the distance, but are actually parallel with each other. Crepuscular rays are sometimes called God's rays, or God's glory. What's the difference between light color and pigment color? We've been talking about how light makes color, because white light is actually made up of the 7 colors added together. And the 7 colors we see in a rainbow are made up of just 3 primary colors of red, blue, and green, or RGB. The reason these 3 are the primary colors is not about physics, but biology and the way our eyes work. There are 3 kinds of color receptors, called cones, inside our eyes. These cones are tuned to be very sensitive to the light wavelengths of red, green, and blue. Red, green, and blue are not made up of any other color, and that's why we consider these as the primary colors. This is also why some people are colorblind. One type of cone is either missing, or they have a different spectral sensitivity, generally not able to clearly distinguish between red and green. Looking at a graphic like this is a typical test for color blindness, where the number 74 either is not seen at all or may be seen as the number 21 by people with color blindness. Here you can see that when the primary colors start to overlap, they mix to produce secondary colors in the rainbow spectrum. They are called secondary because they are made up of 2 of the primary colors. Add the 3 secondary colors together, and you get white light, which you can see here in the middle. Add them in different proportions, and you can get any color of light you want. This is why light is often called color addition. This goes for everything that produces light on its own, like the sun, or stars, or your television screen, a match, computer monitors, a flashlight. You start with black, no light, and then you add colors until you get white. Computer monitors and televisions use a mosaic of red, green, and blue dots or lines. Our eyes do not distinguish the tiny dots, but put a drop of water on your TV or your monitor screen and it will magnify it. Then you should be able to see that the yellow dot, for example, isn't really yellow, but rather it's a combination of red and green dots located right next to each other. Colors are added together for light-producing objects, that is, things that actually make their own light. That's color addition. Add the three primary lights, red, green, and blue, and you get white light. But most objects in the world do not produce their own light. They reflect light. Light hits them, and then the light is reflected into your eye. Things like your clothes, or the house, or the furniture, and the stick. None of these things produce their own light, but instead they reflect light from paint on their surfaces or from the dyes that are naturally inside them. Dyes are also called pigments, from the Latin word that means paint. So why doesn't everything look completely white since all three primary colors are always reflecting off the surfaces? That's because not all pigments reflect all of the three primary colors that hit them. But the apple doesn't look white, even though waves of light that make white, red, green, and blue, are striking it. So what is happening inside the apple pigments? The apple pigments are being very selective and reflecting back only red. The green and blue are subtracted out and absorbed into the pigment. Absorbed. What do we mean by absorbed? I mean, pigments aren't little sponges, so what is really happening to the colors? Well, the truth is, we aren't absolutely sure what is really happening at the atomic level, but we have a pretty workable theory as to what is happening to those colors. Light wave energy physically strikes the apple surface, and the energy is then transferred into the pigment atoms, causing them to vibrate with more energy than they had before. Those vibrations cause heat, which is then dispersed throughout the apple and is never seen as light again. But the red light does not resonate with the atoms in the apple pigments. The red light waves are briefly absorbed, then rejected, retransmitted back out at the same frequency they came in at, red. Thus, when we say that light gets absorbed, what we really mean is that the light energy is changed into heat energy and is absorbed and spread throughout the object, actually making the apple a tiny bit warmer. This is why black cars get hotter in summer than white cars. The light is completely absorbed by the black pigment and transferred into heat energy throughout the car. But the light is almost completely rejected in white, retransmitted back out, just like it came in, and almost no heat energy is created. Pigments absorb all the white light and reject the colors that do not resonate with its particular pigment atoms, and those are the colors we see. Here are the three primary colors, red, green, and blue. When all mixed together, they make white. But what happens when we remove red? Look, the white is gone, and you get this sort of turquoise blue color called cyan, sometimes called minus red. This turquoise blue is what you get when a paint absorbs or eats the red and rejects green and blue. Or if we subtract out the blue, the white turns yellow. because yellow is what you get when a pigment eats or absorbs blue and throws out the red and the green, reflecting them back into your eye. And if you subtract out the green, the white is gone, and you get this sort of pinkish color called magenta. When a pigment eats the green but rejects the red and blue light, you see a pinkish color often called magenta. In fact, magenta is often referred to as minus green. So if magenta is a pigment that minuses out only one color of light and reflects the other two, it must be a primary pigment because it absorbs or minuses only one primary color. And if yellow is a pigment that also only removes one primary color, then it too must be a primary pigment color. And since this baby blue, called cyan, is a pigment that also only subtracts out one primary color, then cyan, baby blue, must also be a primary pigment color also. The primary subtractive colors are the pigments that only take away one of the primary light colors. And those primary pigment colors are cyan, it absorbs red, magenta, it absorbs green, and yellow, it absorbs blue. That's why inkjet printers use these primary pigment colors in your printer: cyan, yellow, and magenta. And since you use a lot of black ink, they mix all three together and give you a separate black cartridge as well.
The combinations can be confusing to remember, but an easy way to remember at least one of the combinations is by looking at a common traffic light. The three primary light colors are here: red, green, and the blue has been subtracted here to the sky background. What remains is in the middle, yellow. Every time you stop at a traffic light, you can say, "Look, subtract blue from red and green, and you get yellow." And I am certain that everyone in the car will continue to be impressed if you do this every time you stop at a red light. It is often taught in schools that the primary pigment colors are red, blue, and yellow, and they are included in children's paint sets, probably because they are brighter and more vivid than the true primary colors of magenta and cyan.
Before the invention of synthetic pigments, the ancients made these pigments from the earth or from living things, and the details of the production of these pigments were a very closely held secret. Deep royal purple came from the slime of this murex marine snail. A deep rich blue was made by crushing the semi-precious stone lapis lazuli. Burnt sienna was made by burning a unique clay found in Siena, Italy. Carmine red was produced by harvesting, drying, and crushing this cactus-dwelling insect. Red, orange, yellow, green, blue, indigo, and violet. They make up the colors of the rainbow, and together they produce white, visible light. In our next segment, we will take a look at mirrors and lenses and answer that all-important question: why does my face look upside down in a spoon?